Today, we're going to break down a fundamental shift happening in AI architecture. It's a move away from a metric that, let's be honest, the entire industry has been obsessed with, toward a new way of thinking that could make the context window itself, well, obsolete. You know the story. For the last 3 years, the big AI arms race has been all about one number: context window size. We saw it go from 8,000 tokens to 100,000, and now we're seeing models with over 1 million. And the whole time, the assumption was pretty simple, right? If you can cram all the data into the prompt, the model will figure it out. Well, it turns out that assumption isn't just a little bit off, it's a trap. It's completely false. When you try to force these huge datasets into a standard model's context window, you don't just see the performance level off. You see it completely collapse. It's a catastrophic failure. And there's a name for this: context rot. It's the systematic breakdown in the model's ability to think straight when it's overloaded. The answers get vague, the costs go through the roof, and the model completely loses the signal in all that noise. The solution, then, isn't a bigger window. It's getting rid of the window altogether. And that solution is coming from some new work out of MIT and Prime Intellect. It's an approach called Recursive Language Models, or RLMs. And look, this isn't just a small upgrade. It's a totally different architecture for how a model should even deal with information. The best way to get this is through an analogy. The old way, what we do now, is like forcing a model to memorize an entire library just to answer one question. It's insane. The RLM approach is totally different. The model doesn't read the input in that same way. Instead, it treats the data like an external document sitting on a desk. This keeps its own working memory clean, focused. It stops trying to memorize, and it starts to navigate. So how does it do that? Well, the process is really methodical. First, it does a quick scan of the input, just to get the lay of the land. Then it starts searching, but selectively. It pokes around for keywords and patterns, and it actively ignores the junk. It breaks down the big problem into smaller, bite-sized chunks. And this is the really clever part. It then delegates the analysis of those chunks to smaller, much cheaper AI instances. And then finally, the main AI just collects all those partial results and puts them together into the final answer. Okay, that all sounds great in theory. But the data is where this whole argument becomes pretty much undeniable. So let's look at the evidence, and we'll start with the total collapse of the old way. This chart right here, this is context rot in action. On a simple task, sure, the model does great. But as you make the task more complex, look at that performance drop. It's a cliff. And on this one benchmark called Ulong Pairs, which is really hard because it forces the model to compare lots of different parts of a huge input, a top-tier model like GPT-5 just dies. Its F1 score, which is just a measure of its accuracy, drops to almost 0. Useless.
Okay, now for the recovery. Watch what happens when we take that exact same model, GPT-5, and just wrap it in this RLM structure. On the code QA benchmark, the base model gets a measly 24%. With RLM, that accuracy leaps to 62%. And remember Ulong Pairs, the task where it completely failed? The F1 score goes from a pathetic 0.04 to a very solid 58. I mean, the performance recovery is just staggering.
And then, of course, there's the cost. On a really complex task, say involving 1,000 different documents, the average cost for a query with an RLM-powered GPT-5 is less than $1. Trying to do that the old way by stuffing everything into the prompt, you're looking at nearly 3 times the cost, and that's assuming the model doesn't just crash and burn before it even gives you an answer. So this begs the question, where is all this improvement actually coming from? To figure that out, the researchers did what's called an ablation study. They started systematically taking parts of the system away to see which component mattered the most. And the results were really not what you'd expect. On that same code QA task, they tested a super simple version with no recursion at all, just the external workspace, and it scored a 66% accuracy. That's even higher than the full, more complicated RLM system. Here's the key takeaway, the big signal. The single biggest performance gain comes from just moving the context out of the model's active memory. That's it. Before you even get to the fancy recursion or delegation, just giving the model a desk to work on instead of forcing it to hold everything in its head, that is the breakthrough.
But look, this is engineering, it's not magic. And the current RLM system definitely has its limits, which the researchers are very open about. The good news, though, is that these limitations are also really big opportunities for improvement. They're basically low-hanging fruit for engineers.
For instance, the costs can swing wildly if the model gets lost and wanders around in the data for too long. The whole thing runs sequentially right now, which makes it slow. Plus, the models haven't actually been trained to do this kind of external navigation efficiently, they're just figuring it out as they go. These are all real solvable engineering problems just waiting for effect. So, when you put all of this together, the implication is pretty clear. The main metric that we've all been chasing for the last few years is quickly becoming irrelevant. We need a new way to measure what these advanced AI systems can actually do. We need to shift our focus from context size to navigation ability. The old question was, how much data can the model hold in its memory? The new question, the one that really matters, is how well can the model find, process, and use data that lives outside of itself? That's the real frontier now for AI reasoning. Which leaves us with one last big question. If a model's real power doesn't come from what it can hold in its head, but from how well it can explore an external world of information, then is the whole race for a bigger and bigger context window already over?